Today I will give a presentation about my main research area about acoustic metagratings for wavefront manipulation. So in recent years, numerous studies demonstrate that conventional gradient metasurface can be used to engineer the acoustic wave propagations based on the well-known generalized Snell's law. In their design space coiling structure as shown at the top figures here, are commonly used to implement the phase gradient by controlling the wave propagating path such that large phase shifts can be accumulated. They enable beam steering, cloaking, and the creation of diffuser by carefully adjusting the phase gradient along the metasurface. However, the efficiency and the resolution of this kind of gradient metasurface approach greatly rely on the level of discretization of the metasurface, and to fully control the phase change, a very dense array of elements is required. Furthermore, the wavefront steering performance can be inefficient due to the impedance mismatch between the incident wave and the wave scatter in the desired direction, especially at very large steering angles. As indicated by the top right figure here, you can see that the beam steering efficiency drops with the increase of the steering angle. Also, most of the design were investigated in auditable frequencies. If the design is applied to ultrasonic range, the complicated internal structure will increase the fabrication complexity and also induce significant thermal viscous losses. Therefore, developing scalable metasurface to control acoustic wavefronts by using ease of fabricate structures still remains as a challenge. In our recent published study, we introduced a new type of metamaterials, which is known as metagratings, to overcome this kind of limitations given by the conventional metasurface. All right, so how does the metagrating work? If we consider the regular reflection, imagine that we just have a hard boundary here. When an incident plane wave hits this wall, it is expected that all of the acoustic wave will be reflected towards the normal direction. But for our metagrating, it is formed by periodic arrays of specially designed meta-atoms, and we use the C-shaped meta-atoms here. And it will reflect the acoustic wave in a different way based on the diffraction theory through the constructive interference. It will generate a number of discrete diffraction orders. And the number of diffraction orders and the corresponding diffraction angles are both determined by the period of the grating, which is indicated by the L here, and also the operating frequency according to this equation. In our recent published paper, we demonstrate that by carefully choosing the meta-atom geometry and their orientation, all energy in principle can be diffracted into a single diffraction order, resulting in anomalous reflection. There are two important design criteria. The first criterion is that the metagrating should be highly reflective. So to achieve this, a hard backing wall is employed such that all incident wave must be reflected while no energy can be transmitted through. And the second design criterion is that the structure should be of asymmetric scattering properties, which is given by the Willis coupling. We can see from this simulated scatter field of a grating, which is formed by symmetric meta-atoms, where the opening of this C-shaped meta-atom is aligned with the direction of the incident plane wave. The reflected pressure field show that it is symmetric about the vertical center line of the unit cell. It means that the reflection towards the -1 diffraction order is the same as the +1 order. Therefore, to engineer the reflected wave into a single particular direction, structure with asymmetric properties is required. So in our design, we achieve this asymmetric scattering properties of the metagrating by twisting the C-shaped meta-atom. And here is the numerical result showing that our C-shaped metagrating can successfully redirect the acoustic wave towards the desired angle around 50 degrees with the efficiency around 99% at 2.2 kilohertz. We have also demonstrated this promising wavefront manipulation capability of our metagrating experimentally in a two-dimensional parallel plate waveguide, which is located at UNSW Canberra. And this setup is surrounded by the absorbing boundary to prevent any reflection inside this waveguide. And we fabricate 6 meta atoms, which were 3D printed, and we use an array of loudspeakers to generate a plane wave. And the acoustic pressure inside this waveguide was measured by a microphone, which is mounted on a belt system. So to apply the oblique instant plane wave, this metagrating was oriented with its surface normal at an angle, and in this case, the angle is 30 degrees relative to the direction of the incidence of the fixed sound source. From the measured angular scattering pattern as shown at the top 2 figures, a main loop towards negative 52 degrees, as indicated by the red solid line, can be clearly seen. And we also measured the 2-dimensional scatter pressure field inside the waveguide, as shown by the bottom right figures here. The beam reflection in this negative 52 degrees can also be seen, which show a very good agreement with the numerical simulations. So our results demonstrate that outstanding beam steering performance of the acoustic metagrating can be achieved, and it can effectively reflect the acoustic wave towards the -1 diffraction order and suppress the acoustic energy towards unwanted directions. And our design is reconfigurable, which enable this high efficiency beam steering for different refraction angle and operating frequency by simply twisting the metal atoms or by adjusting the distance between this metal atom and the backing wall. And also this metagrating approach is also promising for ultrasonic applications, although the metagrating is optimized at a single operating frequency. Such design can be readily adapted for very high frequencies due to the lack of fine features by simply scaling the size. So this outstanding wavefront manipulation characteristics of our metagratings offer a promising design framework to passively focus the acoustic beam with scalable structures. Here we demonstrate that an efficient metal lens can be realized using adiabatically varying metagratings. Unlike the conventional gradient metasurface-based lenses, we perform this beam focusing by locally control the excitation of a single diffraction order and without attempting to engineer the continuous phase distribution. This working principle can be realized in a one-dimensional lens, as shown by this figure here. Given the focal length YF, the corresponding spatial reflection angle along the lens can be calculated by using this equation. And the figure on the right here shows the example of how does the profile of the reflection angle along this right half metal lens should look like when the focal length is equals to 30 lambdas and the operating frequency is 40 kilohertz. So to perform this angle manipulation, we apply the metagrating concept, which locally varying the diffraction angles along the metal lens. Here we propose a multi-layer step metal atom, which can be analytically optimized by using the genetic algorithm to form the local metagratings. Taking the Y-angle covering advantage of this proposed metagrating structure, 4 scatterers designs are already enough to provide effective beam steering with efficiency larger than 0.9 for refraction angle from -38 degrees to -76 degrees at 40 kilohertz. So the right half meta lens can therefore be implemented by combining the optimized local metagratings, which satisfy the reflection angle profile as identified the first step. And in this work, we consider the focal spot to be located at x equals 0, which is aligned with the center of the meta lens. Therefore, the full meta lens can be obtained by mirroring this right half lens about x-axis equals to 0 and combining this mirror structure with the original one. Here shows the performance of the proposed metagrating-based lens for two different focal lengths, YF equals to 7 lambdas and 3.5 lambda respectively at frequency equals to 40 kilohertz. The top two figures shows the numerical simulated intensity field generated by two different metagrating lenses when a normal plane wave incident is applied to the structure. We can clearly see that the acoustic energy is effectively converged to a desired focal spot for both cases, and the figures below show the intensity profile extracted from the focal plane, which is indicated by this white dashed line. The results shows that our proposed metagrating approach can successfully achieve acoustic focusing in ultrasonic frequencies, even for different focal length. To validate our metagrating-based design principle, we conduct an experimental study of our ultrasonic meta lens inside an anechoic chamber with the setup as shown on the left figures. A single ultrasonic transducer is used to generate the incident wave at 40 kilohertz, and the transducer is slightly shifted from the y-axis of the metal lens to suppress the multiple reflection between the lens and the transducer. So significant intensity enhancement at the focal spot can be observed from the experiment, which is nearly 22.9 times of the incident one, and the profiles of the normalized intensity on the focal plane show by the bottom figures. It shows that our experimental results are in good agreement with the numerical prediction as indicated by the black dashed line. So to conclude, in this study, we introduced a new acoustic metagrating to perform high-efficiency beam steering. With the promising wavefront manipulation capability of metagrating, we introduced a new design principle of meta lens for acoustic focusing. This metagrating approach can be adapted to perform acoustic focusing for different operating frequencies and focal lengths, which may facilitate the further development of a wide range of applications such as acoustic levitations or teleology used in ultrasonic imaging. So that's all for my presentation. Any comments or suggestions would be greatly appreciated. Thank you.
Well, thank you for